Every second, a whopping 40 kilograms of water vapor rushes out from Comet 3I/Atlas. That's what NASA's Swift Observatory picked up in late July and early August. And this wasn't even at its closest approach to the Sun. Not during that intense solar embrace where radiation peaks. No, this was at 2.9 astronomical units away, nearly 3 times Earth's distance from the Sun, where you'd expect barely any ice to turn to gas. Then, in under 3 weeks, it slips behind the Sun, out of sight from all Earth-based scopes, just as the action ramps up. Want the latest on what unfolds? Smash that like button and subscribe. Drop a comment with your location, the local time, and your take. Is this wild outgassing or something more mysterious? Chapter 1. The Fire Hose Enigma. The Swift data, released on September 30th in Astrophysical Journal Letters, doesn't just stand out. It's shattering expectations. Dennis Bodix and colleagues at Oren University dedicated more than 2 hours to layering ultraviolet images, zeroing in on the hydroxyl signal, that signature shimmer from sunlight splitting water apart. Their discovery? A vapor release rate that ignores standard distance models. Comets at that solar distance usually exhibit just 3 to 5% active surface. But 3I/Atlas? At least 8%, almost twice as much. Yet that's not the weirdest part. The numbers don't add up for straightforward ice evaporation from the surface, not even factoring in the sun's warmth at 2.9 Australian dollars. The available energy simply can't account for 40 kilograms per second from a core roughly 5 to 6 kilometers wide. Something extra must be at play. Infrared scans from Gemini South and NASA's Infrared Telescope facility offered clues. Ice fragments drifting in the coma beyond mere gas. Real solid bits of ice lingering in the haze around the core. When sunlight, even faint rays, hits them, these pieces warm quicker than the main body thanks to their greater surface-to-volume ratio. They turn into tiny geysers. With hundreds or thousands dispersed in the coma, they boost the overall water flow. It makes the comet seem way more vigorous than its actual surface activity. Zhi Xing, the principal researcher, summed it up neatly. Every interstellar visitor we've spotted has thrown us for a loop. Oumuamua was arid. Borisov brimmed with carbon monoxide. Now Atlas is shedding water far out, against all forecasts. They're all reshaping our understanding. So, what's behind those ice bits to begin with? Did 3I/Atlas undergo some breakup before we spotted it? Could this be fallout from eons of tiny meteor hits on its cosmic trek? Or do galactic thick disk comets just operate differently, built in environments our solar system never saw? The schedule complicates things further. 3I/Atlas dropped out of Swift sites in August, too sunward for secure viewing. But come early October, ESA's Mars probes nabbed it at 30 million kilometers during a close pass. The coma stretched visibly across thousands of km, confirming the outburst held steady. It's still leaking water as perihelion nears. And nears is key here. Right now, 3I/Atlas is diving into solar conjunction. With Earth and the comet flanking the Sun oppositely, no Earth telescope can pierce the brightness. It'll hit perihelion on October 29th at 1:36 Australian dollars, snug inside Mars' path, totally obscured from us. The Sun's rays there pack way more punch than what Swift measured, orders of magnitude fiercer. If 40 kilograms per second marked the norm at 3 Australian dollars, imagine the surge at 1.4. Conventional wisdom says it'll flare up big time. The coma will balloon. Hyperactive ices like CO2 and CO, which vaporize cooler than H2O, ought to burst free. The tail could unfurl into a dazzling ribbon spanning millions of kilometers. We've witnessed this routine countless times in homegrown comets. But 3I/Atlas has already ditched the script. That distant water surge? Unheard of. The 8% active area? Off the charts. The frozen rubble in the coma? Total surprise. So the veiled perihelion phase? Pure speculation. ESA's JUICE probe gets prime seeding from November 2nd to 25th. Once 3I/Atlas swings back into view, JUICE will scan it using imagers, spectrometers, and detectors. Its position is ideal, distant enough from the Sun for clear sights, yet near enough for sharp post-perihelion details. The catch? Getting the info home. JUICE is flipping its high-gain dish into a sunshade at the moment, stuck with a low-speed secondary antenna for Earth links. Those November captures won't reach us until February 2026. 90 days of uncertainty. 90 days wondering whether the comet made it through perihelion unscathed, whether it splintered apart similar to Shoemaker Levy 9 due to Jupiter's gravitational pull, or if some unforeseen event unfolded during those concealed moments obscured by the sun. There's one additional factor, casually noted by Dennis Boditz without much focus. Water serves as the key metric in comet research. It acts as the standard for gauging activity levels and deducing makeup. Yet, 3I/Atlas isn't a typical solar system comet. It's an envoy from a distant star's planetary setup, one that originated possibly 10 billion years back in the galaxy's dense disk. The primordial disk spawning this body featured distinct temperatures, varying makeup, and unique chemical variations compared to the disk that birthed Earth and Jupiter. The water we're spotting could chemically match our hydrogen and oxygen in the usual setup, yet its background is utterly foreign. The isotope proportions, the minor elements blended in, the very formation of the ice grains. All these hold clues to a stellar system beyond our reach. Swift picked up hydroxyl, the shattered leftover from water molecules. However, hydroxyl can originate from various source molecules too. Organics, alcohols, intricate reactions unfolding in the coma where solar radiation and cosmic particles dismantle bigger compounds into bits. That 40 kilograms per second could represent pure water or a blend of water alongside other gases yielding comparable spectral signs. We require finer spectroscopy to confirm. We need extended viewing periods. We need the comet to endure perihelion and keep venting as it recedes into interstellar realms, for that's the harsh truth. 3I/Atlas won't return. Once it swings by Jupiter in March 2026, it's gone for good. This marks our sole opportunity to examine a comet from the galactic thick disk, a group of ancient stellar groups we've yet to probe. Each sighting counts. Every bit of data is priceless. The torrent of water vapor is merely the prelude. It reveals 3I/Atlas brims with volatiles, exhibits odd structural traits, and releases gas at ranges where local comets stay quiet. But the real drama unfolds over the coming month, concealed behind the sun out of sight, where comet norms could hold firm or break apart entirely. And when JUICE secures its readings in November, as the comet reappears bearing the full scars of perihelion, we'll discern if this water ejection was a teaser or a red flag. We'll determine if 3I/Atlas is simply an unusually lively comet or a discovery demanding a full overhaul of our scientific texts. The resolution lurks unseen, just 50 days from unveiling. Chapter 2. Lowe's Mothership Idea. The Loeb scale score shifted from 4 to 6 over a mere 2 weeks. That's no minor increment. On a scale running from 0 for purely natural to 10 for clearly artificial, advancing from 4 to 6 signals a major reevaluation of likelihoods. And Lowe rarely adjusts ratings casually. Every notch demands concrete irregularities, data points that defy standard interpretations. By mid-August, 3I/Atlas had gathered sufficient oddities to nudge the gauge into realms that unsettle most researchers. I'll begin with the trajectory odds, repeatedly highlighted yet often brushed off. 0.005%. That's the chance a random interstellar intruder would skim as near as 3I/Atlas to Venus, Mars, and Jupiter. 1 in 20,000. Lowe's group derived this via orbital calculations and alignment slots, factoring in planetary motion and the slim margins for close passes. The equations are basic. An inbound body on a backward hyperbolic path from Sagittarius direction has a narrow chance funnel for each planet brush. The joint odds of nailing all three are minuscule. Detractors claim we're selecting data post-discovery, that scanning enough interstellar wanderers means one will eventually show an improbable path purely by luck. Fair enough, but we've only spotted 3 such visitors to date, and one pulls off the feat of grazing the solar system's 3' inner rocky worlds. The baseline assumption for that, the prior odd sans other proof, is troubling. Now layer on the perihelion schedule. October 29th, solar conjunction, with Earth and 3I/Atlas positioned opposite across the sun. No terrestrial telescopes can track it through the pivotal stretch. If aiming for a thrust adjustment, an engine pulse altering speed and path, perihelion offers the prime spot. You're racing at peak velocity against the sun. Thus, each unit of fuel delivers maximum. The Oberth effect delivers the maximum change in velocity. Spacecraft rely on it all the time, and Comet 3I/Atlas hits perihelion exactly during the period when solar glare hides it from view. Low figured out the velocity shift needed for tiny probes launched at that closest solar approach to make it into Earth's orbit. The math checks out. A compact probe, say around 10 kilograms, equipped with a chemical engine boasting a specific impulse of about 300 seconds, could execute an inverted Oberth maneuver and settle into a reliable Earth orbit. The timing for arrival lines up with late November through early December, just as 3I/Atlas swings out from behind the sun and observers begin scanning for alterations after perihelion. Could this be intentional? Or are we just imposing order on chaos because our brains are wired to spot connections, especially since the recent visitor has tuned us to hunt for precisely these signs? The puzzle over its dimensions lingers. Initial light readings pointed to a 20 kilometers core, assuming average asteroid reflectivity. That's ridiculously oversized for something from outside our system. Oumuamua measured just a few hundred meters across. Borisov stayed below a kilometer. A 20 kilometers interloper comet invading our neighborhood would defy statistical odds. It's the sort of rarity that shouldn't occur within a single generation. Yet Hubble's views of the surrounding haze revised those figures downward. Now it's pegged at 5 to 6 kilometers, drawing from the core's glow relative to the overall brightness of the dusty envelope. That's still substantial, still atypical, yet feasible for a cosmic wanderer. But those first brightness spikes weren't mistaken. They were genuine. 3I/Atlas truly shone brighter than expected for a 5 kilometers body at such a range. Low proposes enhanced reflectivity, a surface laced with metals, a form that channels sunlight efficiently, or compositional traits far from the usual fluffy ice and grit. All could explain the excess gleam. All could make it seem larger than reality. That's plausible in nature. We've cataloged metallic asteroids before. Still, when stacked with the other oddities, it tips the scales toward higher odds of artifice. Consider the dust pattern too. Hubble snapshots reveal the thickest concentration on the solar-facing flank. The heftier particles, immune to solar radiation's shove, cluster in front of the core along its path. Typical comet venting generates streams at right angles to the surface, driven by spot heating. Those streams veer unpredictably, shaped by spin axis and ice patch layouts. Persistent dust blasting toward the sun, though, demands an oddly aligned spin or an alternative mechanism, one that steadily flings matter forward, no matter which side greets the sunlight. Low highlights how this aligns with debris kicked up during a blistering interstellar dash. At 60 to 70 kilometers per second over eons, collisions with hydrogen atoms in space pack real punch. Cumulative hits would sculpt the forward face through erosion. The observed dust might stem from such battering, bits perpetually sheared away by the onslaught of interstellar drag as the thing barrels onward. That's a straightforward natural account, yet it dovetails neatly with exhaust from onboard tech. Say, thrusters for keeping steady amid maneuvers that mimic those signatures. The 16.16-hour spin cycle lands squarely in a gray zone, not rapid enough to accelerate from gas release, yet too brisk for gravitational capture by any body. For a loosely bound pile of rubble, sustained by feeble self-pull, it's routine and steady. For a denser, whether organic or engineered, it's just as mundane and balanced. It reveals zilch conclusive. The incoming trajectory proves tougher to wave off. Originating in Sagittarius aligns it with the galactic core's dense, luminous sprawl. Picking it out against that glare is a nightmare. We only nabbed 3I/Atlas thanks to the Atlas survey's tailored hunt for speedy intruders, and even so, it almost slipped away. Retrospective images traced to mid-June, but weeks prior, at magnitude 20, it was a faint whisper, and we'd have zero data otherwise. It would have threaded the solar system's heart unseen. For a scouting run into a foreign star system, entering via the galactic hub makes strategic sense. You slip in shrouded by stellar noise, offering locals scant alert. By detection time, you're entrenched inward, rendering reactions futile. Was that the ploy? or yet another instance of weaving purpose from happenstance? The initial spectral mix-up layers on more intrigue. Several groups found no carbon compounds in those opening weeks. No distinct water traces, merely rusty grains and hazy spectral dips. It seemed dynamic yet uncomet-like. Lowe contended that clinching evidence showed that 3I/Atlas wasn't acting like a typical comet. Additional data soon followed. Traces of water appeared. Carbon dioxide overwhelmed the surrounding haze. The light patterns began aligning with what we'd expect from a comet. Lowe adjusted his stance, though he pointed out the early uncertainty still lacks a clear explanation. What delayed the emergence of those usual icy gas signals? Why the initial mix-up? Perhaps it stemmed from detection limitations. Initial scans were rough, quick shots captured while the object remained dim. Once it grew brighter and sharper tools focused in, the readings sharpened. The apparent lack of gases was merely a shortfall in clear, strong data. That's the straightforward explanation. It's likely the right one, though likely carries heavy weight there. Lowe isn't asserting absolute proof. He's arguing that the chance isn't zero, and the fallout from airing, from brushing off a possible engineered item as just another comet, given how routine comets are versus rare relics, could shatter our grasp of cosmic minds. He urges the Galileo project's facilities to scan for follow-up clues through November and December. Should 3I/Atlas dispatch smaller units? Or if those units plunge into our atmosphere for a detailed look at Earth, we could see a surge in unexplained flying objects. Items zipping along paths that ignore standard flight physics. Radar blips that don't fit rocks or our own machines. Is this probable? Hardly. Lowe concedes the scales tip toward a plain old comet, yet they're far from absolute. And in that sliver between strong odds and total surety dwells the whole realm of searching for alien-made signs. For 6 decades, we've tuned in for radio chatter from extraterrestrial societies. We've erected giant scopes to spot laser pulses from far-off suns. We've sifted through countless starlight profiles hunting for life traces in alien worlds' airs. But we've rarely pondered that relics could visit us. That visitors from between the stars, the kind we've only begun spotting over the past 8 years, might mix scouts with mere stones. 3I/Atlas serves as the proving ground, the visitor compelling us to craft ways to tell organic from crafted across vast gulfs. Such tools don't exist. We rely on light variations, color profiles, and path breakdowns, but we lack a solid system to declare this purely cosmic or this demands deeper scrutiny. Lowe is forging that system on the fly, with 3I/Atlas as the benchmark. The idea of a carrier vessel is sleek, yet chilling. You wouldn't dispatch a single scout to a lone sun. Too wasteful. Instead, you launch big carriers on gradual paths linking promising stellar clusters. Every carrier hauls scores or hordes of tinier scouts. Nearing a system, it deploys customized scouts for key worlds. Those scouts are disposable, compact, easy to produce. The carrier presses onward to the following sun and beyond, charting the galaxy across eons. To its builders, the payoff is huge. A single carrier could probe thousands of realms, and we'd miss its approach entirely. The carrier stays shadowed, frigid, blending with comets or space rocks until deployment begins. At that point, it's finished. The scouts are loose, heading to objectives, and even spotting them wouldn't let us catch up. Not with today's gear, unless we'd had years to prepare. Lowe sketched a schedule. Suppose scouts launched on October 29th amid the obscured close solar pass, breaking via backward planetary slingshots to snag Earth orbit. They'd reach us from November 21st to December 5th. We're eyeing items perhaps shoebox-sized or tinier. Our planetary watch systems spot down to roughly 10 centimeters in close orbits. But that's for anticipated items on known paths. Something arriving from deep space, with steering and thrust, could slip right past. Will they reach out? Stay stealthy? Circle above to watch, touch down, or just log and relay? Those puzzles haunt Lowe's sleepless hours, as the response shapes it all. If they're benign seekers, the field researchers of an old star-spanning culture, initial encounter might rank as humanity's pinnacle. If they're otherwise, if the shadowed woods theory holds and broadcasting your spot invites doom, we could already be past the point of no return. The Galileo project sites stand ready. 3 locations, Round-the-clock vigilance, sweeping the whole sky. Any oddity, any incidents occurring within the November-December timeframe will be recorded, examined, and shared publicly. Should nothing occur, if 3I/Atlas simply acts like a typical comet and no spacecraft show up, the theory will lose its validity. The anomaly rating for the lobe structure would then decrease significantly. We'd categorize 3I/Atlas as intriguing yet entirely natural and proceed accordingly. However, if events do unfold, if we spot entities that defy expectations, traveling in improbable trajectories, materializing precisely as low forecasted, then we're faced with either a challenge or a breakthrough, hinging on subsequent developments. Chapter 3, October 29th, Hidden Behind the Sun. This solar conjunction shouldn't be so intense. Typically, comets swing behind the sun, vanishing from sight for days or weeks before reappearing on the opposite side, altered in predictable ways, more luminous if intact, broken apart if not. For centuries, astronomers have observed this cycle. We anticipate the outcomes. Yet 3I/Atlas will hit perihelion at 1:36 astronomical units on October 29th, fully obscured by the sun's blinding radiance. The ensuing doubt about its fate is pushing researchers into unfamiliar ground. The setup is unforgiving. With Earth and the comet positioned on contrary sides of the sun, the angle prevents any earthbound viewing. Aiming a telescope at something just 12 degrees from the sun risks ruining the equipment or overwhelming the sensors. The solar brightness drowns out all else. Even orbital observatories like Hubble adhere to rigid no-go zones near the sun. Instruments such as SOHO and other coronagraphs could offer a brief look, but 3I/Atlas is projected to be too dim and distant from the sun's edge to stand out amid the diffused glow. For roughly 6 weeks, spanning early October to mid-November, observation remains impossible. Perihelion involves more than just sight lines. It's rooted in physical processes. At $1.36, the sun's energy is potent enough to evaporate all icy materials on the comet's exterior. Water ice turns to gas with vigor. Based on JWST's findings, carbon dioxide, the main gas in the coma, shifts from solid to vapor in an instant. Along with it, carbon monoxide, ammonia, methane, and other exotic ices embedded within release all at once. The core ought to turn into a high-pressure vessel. Gases jetting out via fissures and outlets, particles raised by the growing fumes, the coma ballooning to millions of kilometers. The tail trailing like a flag in the wind. That's the standard prediction, straight from every reference manual. This framework presumes a solid grasp of 3I/Atlas's makeup and build, which we lack entirely. Data from JWST on August 6th exposed a surprise, an 8:1 proportion of carbon dioxide to water. That's one of the most elevated ratios detected in any comet. Comets in our solar system usually display balances nearer to 1:1, or even water-heavy compositions. CO2 is typical, but seldom the chief driver. 3I/Atlas reverses that dynamic. It's essentially a dry ice body, with water playing a supporting role. This alters the entire picture of perihelion dynamics. Dry ice sublimates at far cooler temperatures than water ice. At $1.36, the sun-facing surface might climb to 200 Kelvin or more. That's plenty above CO2's activation threshold of about 150 Kelvin. Water ice, by contrast, requires around 270 Kelvin for effective sublimation. Thus, a separation emerges. CO2 blasts away from the surface right away. The water, whether layered beneath or blended in, vaporizes at a more gradual pace. This leads to a phased release of gases, an initial explosive surge of CO2, forming a vivid, swiftly growing coma, followed by a steadier emission of water vapor as outer layers wear down and reveal inner reserves. Yet complications arise. If CO2 prevails and erupts with force, it might strip off the protective dust covering the deeper water ice. Without that barrier, sunlight reaches further in. Water evaporation then speeds up. In hours or days, the comet could shift from CO2 lead to water-led behavior, and we'll miss the transition entirely. Only JUICE's November scans will reveal the results. Then there's the unspoken possibility, avoided in official publications, but murmured in private discussions, fragmentation. The stresses of perihelion are genuine. Thermal jolts, gas buildup inside, and the sun's gravitational pull can rip fragile bodies to shreds. History bears this out. Shoemaker Levy 9 broke into over 20 fragments before crashing into Jupiter. Comet Biela divided in the 1800s and stayed in pieces. More lately, Comet Atlas C/2019Y4 crumbled in 2020 nearing the Sun, dissolving into a haze of rubble. 3I/Atlas spins once every 16 hours. That's leisurely enough to dismiss spin-related breakup. Its own gravity should keep it cohesive. But the body has been journeying across the void between stars for billions of years. The battering from cosmic rays, wild swings in temperature from almost absolute zero up to the faint heat it snagged while gliding past distant suns, collisions with tiny space rocks, and hollow spaces carved out inside from gases escaping over eons. Damage to its framework might lurk in spots that spectroscopy or light measurements can't pick up. Should it break apart, the brightness pattern would reveal it. A quick surge in shine as fresh surfaces uncover, followed by a sharp dimming once the pieces spread out and the overall reflecting area shrinks. Come November, when Juice takes a look, Weed spots several clumps, distinct cores, each trailing its own hazy envelopes stretched along the path. From a research standpoint, that'd be incredible. Bits from deep inside an interstellar wanderer, various strata revealed, chemical differences across its layers on full display. Yet it would also signal we overlooked the actual splitting moment. The breakup instant, the stresses at play, how the stuff came undone. None of that unfolded in view. It all went down hidden by the sun's blaze. Then there's Lowe's idea, viewing the sun's closest approach as a chance instead of a risk. Suppose 3I/Atlas is artificial, equipped with engines or steering controls. Perihelion's your prime time to fire them up. The solar gravity boost multiplies the push from every bit of fuel. A brief burst there yields speed shifts that'd demand way more propellant elsewhere, like at aphelion. For launching scouts to snag planetary paths, this is the spot to let them go. The numbers don't lie. October 29th marks the sweet spot. Low crunch the specifics. A 10 kilograms device with a chemical thruster delivering 500 meters per second velocity change could slot into a stretched-out Earth trajectory, dipping to about 400 kilometers at closest and stretching past the moon at farthest. Parked there, it might probe Earth's air layers, seas, radio signals, or any orbital sites. It could beam findings back to 3I/Atlas prior to the main craft fleeing the solar system. Or stay quiet, lurking, watching, logging info for eventual pickup. The entry slot falls in late November, from the 21st through December 5th, based on launch spot and course tweaks. That's figuring the scouts make just essential nudges en route. With extra propellant or smarter navigation, that time frame widens. They might show up sooner or stretch it out. We could totally overlook them if they dodge by steering clear. And here's the tricky bit. Would we even clock them as unusual? Our orbital watch system logs known items. Man-made satellites, junk, dead boosters. We predict their spots via gravity rules. A fresh arrival in some odd path would set off warnings. But reactions aren't immediate. While we're pinpointing the oddity, tracing its source, dismissing cosmic causes, the scout might wrap its key tasks and shift paths anew. Lowe's got the Galileo Project scopes hunting precisely for this. 3 locations doing non-stop sky sweeps across visible light, heat signatures, and radio bands. Any fleeting blip or thing zipping off predicted paths gets queued for review. Over the November to December stretch, they'll dial down the alert bar. More false alarms, sure, but heightened catch rate too. Should anything drop in, it'll get spotted. NASA and ESA haven't weighed in publicly on this angle. They're sticking to the everyday comet theory, though privately, folks are tuned in. Space outfits have routines for mystery items. Not sci-fi alien stuff, but practical steps for rogue wreckage, unlisted orbiters, crash risks. Those can flex to fit. An Earth orbit intruder sans launch record, no database listing, no obvious spaceborne routes. It kicks off the procedures. Monitoring ramps up. Defense gear joins in. Global players start probing. With this recording dropping live, October 29th is just 6 days out. 3I/Atlas has vanished, lost in the sun's glow. Final Earth telescope views came in late September. Red Planet satellites nabbed it on the October 3rd flypast, but pics depicted a standard comet. Clear haze, dust kicking up from sun warmth. No weirdness hinting at tech, breakup, or trouble. Still, perihelion changes everything. That's where heat strain maxes out, where built-up forces overpower the build, where choices happen. If choices exist at all, in 6 days, 3I/Atlas will hug the sun tighter than any time in its billions-year run. Surface heat will soar. Gas release will surge wildly, and none of it plays out in sight. The SolLive updates will code data from sun-watching satellites like Stereo and SOHO could potentially pick up traces. The Parker Solar Probe isn't in an ideal spot for this. Yet, through scattered light and shifts in brightness, these instruments might register activity. Should Comet 3I/Atlas unleash a significant flare-up or its envelope swell quickly, the solar surveillance probes may spot alterations in the reflected sunlight. Such signals would come indirectly, at coarse detail, but they'd offer a vital clue amid the data blackout. Next, anticipation builds for JUICE's input. The probe sits ideally placed to scan the comet after its solar closest approach. From November 2nd through 25th, it'll deploy various tools. Janus imagers for visuals, a key spectrometer to probe makeup, the PEP sensor for the surrounding gas shell, and the UVS device to spot fleeting compounds. Everything trained on 3I/Atlas as it swings out from the sun's shadow, still aglow from the heat, possibly broken apart, maybe sporting a stunning trail, or perhaps pulling off an unforeseen twist. However, that information won't reach us until February 2026. Currently, JUICE deploys its main antenna as thermal protection, using the secondary one for signals. Bandwidth remains limited. Recording trumps sending, so visuals and readings accumulate internally, queued for later transfer when capacity frees up. When we finally review JUICE's November captures, 3I/Atlas will have zipped beyond Venus, en route to the outer belt, already dimming and losing warmth. A 3-month delay sparks debates, rival theories, and heated discussions. Intact or shattered? Any oddities in the concealed solar flyby? The truth lingers in light-speed particles racing from JUICE to our planet at this very instant. Yet it's locked away. Knowledge stays out of reach until the files land, undergo review, and roll out to scientists. That's the price tag for probing deep space via inter-system craft. Extraordinary perspectives from prime locations, offset by delays, suspense, and doubt lingering for months, not mere hours. October 29th marks the turning point. Prior to then, 3I/Atlas remains a sunbound wanderer, odd yet understandable, engaging but not game-changing. Post that, it transforms into perihelion's creation, a shattered rubble cloud, a vivid body with an enormous streamer, a quiet survivor, holding together yet hushed, or an entirely fresh entity demanding revised labels, concepts, and analytical paradigms. Solar glare conceals the outcome, not eternally, merely sufficiently to render the suspense excruciating. Chapter 4. The CO2 Puzzle. The James Webb Space Telescope targeted 3I/Atlas on August 6th, when it was $3.32 Australian dollars from the sun. Its NIR-SPEC tool, built to snag infrared traces beyond visible scopes, gathered spectral scans from 0.6 to 5.3 microns. The results weren't merely peculiar. They revealed a molecular makeup absent from our comet archives. A 7.6 to 1 ratio of carbon dioxide to water. To put it in perspective, the runner-up, barring the wild case of C/2016 R2, falls under 3:1. 3I/Atlas doesn't just carry ample CO2. It's overwhelmingly ruled by it, in ways that upend our ideas on how comets assemble. Martin Cordner of NASA Goddard headed the review group. Their report, posted to AR-14 in late August, details the findings thoroughly. The gas envelope displays boosted venting toward the daylight face, just as solar warmth would drive. H2O shows up. CO is there. Hints of carbonyl sulfide emerge. Frozen water glints in the lines. Grain reflection appears in near and mid-infrared. Everything standard. Everything aligning with typical comet traits, save for that proportion. At 7.6:1, or 6:1 rounded, it's 4. 5 sigma beyond the baseline for distant and Jupiter orbit comets at comparable sun distances. Statistically, sigma gauges deviation from the norm. 1 sigma, everyday fluctuation. 2, noteworthy. 3, uncommon. For 0.5 sigma, either a major glitch or a core distinction. With outliers this extreme, doubts arise about the validity of your baseline dataset. Perhaps 3I/Atlas isn't the exception. Maybe it's from a distinct group, like pitting apples against non-produce. The carbon isotope levels provide further insight. JWST picked up C12 and C13 in the gas outflows. Their balance matches patterns on Earth and across the solar system. This points to origins in a familiar stellar setting, not some ancient triple-star system with scant metals, nor a star bloated with bizarre fusion yields, just everyday carbon from a standard sun. Still, the CO2 overload compared to water spins a contrasting tale about scientists remain puzzled about the origins and formation of the ice in this comet. 2 main theories attempt to explain it, though each faces significant challenges. One hypothesis centers on radiation effects. Should the comet have originated in a protoplanetary disk bathed in powerful ultraviolet light from a young, scorching star, or endured billions of years traversing the interstellar medium under constant cosmic ray assault, its water ice might have been selectively eroded. Water molecules prove more fragile than those of carbon dioxide, making them simpler to dismantle. Energetic photons and particles strike the ice, severing the hydrogen-oxygen links, while the lightweight hydrogen drifts away into space. The leftover oxygen might then bond with carbon to yield additional carbon dioxide. Across eons, a comet starting with ample water could evolve into one dominated by CO2 simply through relentless degradation. Yet this idea falls short on a numerical level. Transforming a comet from a balanced mix of water and carbon dioxide to an 8:1 imbalance in favor of CO2 demands extraordinarily intense radiation over vast timescales. We're considering billions of years adrift in the interstellar void, devoid of any protection. This fits the comet's possible antiquity, but it hinges on the water ice staying fully exposed on the surface throughout. Should a dust mantle or internal barriers shield underlying ice from the onslaught, the alteration process would plummet in effectiveness. A layered effect emerges. Outer ice thoroughly altered, inner ice untouched. As the comet activates and peels away outer layers, the composition ratio ought to shift with fresher material revealed. So far, no such variation has appeared. The proportions stayed steady from the August JWST readings to the prior SphereX results. The alternative theory focuses on where the comet formed. Carbon dioxide solidifies at a cooler temperature than water does. Within a protoplanetary disk, a demarcation known as the CO2 ice line exists. Inward of it, CO2 stays as gas. Beyond it, it freezes solid. The water ice line lies nearer the central star. If the comet assembled past the CO2 ice line in a disk unusually laden with carbon, it might have naturally gathered more CO2 than water right from the start. This imbalance would lock into the comet's makeup immediately upon formation. However, this demands particular circumstances, a protoplanetary disk boasting an elevated carbon-to-oxygen ratio, or one whose thermal profile positioned the nascent comet in a CO2 ice abundant region but water ice scarce. Such setups occur as stellar compositions and disk architectures differ widely, though achieving precisely an 8:1 ratio isn't straightforward. It calls for precise calibration, a stellar environment markedly unlike our solar systems, one that's uncommon yet feasible. Data from SphereX in mid-August bolsters this view. The Infrared Space Observatory spotted a vast CO2 plume stretching over 348,000 kilometers from the core. No equivalent water plume extended that far. CO2 jets out more vigorously, reaching greater distances and shaping the coma predominantly. In contrast, water output stayed undetectable for SphereX, capped at roughly 4.5 kilograms per second. That's fully 10 times less than Swift's reported 40 kilograms per second, a figure already dubious due to observational range and techniques. This inconsistency highlights a key point. Spotting water is tricky. It needs targeted wavelengths and tools. Swift picked up hydroxyl, a dissociation byproduct rather than direct water. SphereX scanned for infrared water emission features, but found none. JWST did detect water, albeit far less abundant than CO2. Every instrument captures a unique aspect of the enigma. Harmonizing these demands inferences on chemical reactions, photodissociation speeds, and material spread, none firmly established for an interstellar wanderer of obscure makeup. A striking feature from JWST's findings merits note. Water emissions at 2.7 micrometers display uneven patterns across the coma, not a smooth spread, but clusters of bright and faint areas, hinting at focused outflows, maybe jets or enclaves of water-laden ice embedded within a CO2-heavy framework. When sunlight hits these zones, water bursts forth sporadically instead of via consistent evaporation. This yields irregular patterns in the spectra. By comparison, CO2 emissions at 4.3 micrometers appear more uniform, spread evenly, aligning with broad sublimation over the sun-facing side. This contrast in distribution points to a complex internal makeup for the comet. Were it uniformly CO2 ice, outgassing would proceed evenly everywhere. The patchy water signals imply diversity, segments, strata, or inclusions of varying makeup, akin to rock formations with separate bands. Every stratum capturing a unique phase in the comet's history. The development or progression of the comet isn't solely tied to its core makeup. As erosion wears away the outer layers, various strata become visible, altering the gas output in response. Yet an alternative explanation exists. The concentrated water vapor might originate from the frozen rubble scattered in the coma. These are the identical fragments that Swift spotted indirectly via hydroxyl signatures. Should those pieces vary in makeup from the central nucleus, say, some loaded with water while others brim with carbon dioxide, the uneven distribution aligns logically. What appears as features on the nucleus could actually be patterns within the encircling dust and gas. Picture scores or even thousands of icy fragments, each acting like a tiny comet, adding to the overall emissions in distinct ways. To differentiate these views demands sharper imagery. Resolving the nucleus proper is essential to spot any active zones, jets, or targeted outlets spewing gases. Hubble falls short. The core is minuscule and distant. JWST struggles too. Its view is too limited, and the comet's speed hinders thorough scans. JUICE could manage it come November, provided the object glows brightly, draws near, and the instruments lock on steadily, though that's far from guaranteed. The provisional spotting of carbonyl sulfide layers in further intrigue. OCS rarely shows up in solar system comets. It pops up sporadically, typically in trace amounts, hinting at sulfur processes in the protoplanetary disk. If 3I/Atlas carries detectable OCS, it implies sulfur was present in its birth star system amid planetary buildup. Paired with the heavy carbon dioxide presence, this sketches a stellar setup with odd volatile balances. Elevated carbon, notable sulfur, diminished oxygen, or at minimum, reduced water. A realm favoring reduced molecules over oxidized variants. Why is this significant? Volatile compositions shape potential for life. A system flush with carbon dioxide and sulfur, yet starved of water, offers slim odds for biology as we know it. Water serves as the key solvent, the arena for chemical reactions in living systems. Carbon dioxide has its roles. Think photosynthesis in plants, but it can't stand in for water. Should 3I/Atlas have originated where water was sparse, its systems worlds would grapple with profound hurdles for fostering or preserving life. They'd be arid realms, abundant in carbon but deficient in H2O. Much like the emerging discoveries orbiting M dwarfs, those compact red stars that outnumber others in the galaxy. Could that be 3I/Atlas's provenance? An M dwarf environment where the life-friendly zone hugs the star tightly. Tidal forces scorching one face while icing the other. Where water stays rare and carbon dioxide rules the air's makeup. This aligns with the thick disk heritage. Ancient stars, generally lower in metals, yet showing broad diversity. M dwarfs born 10 billion years back, still fusing steadily, as their orbiting bodies adapted, or didn't, amid tough circumstances. Mind you, this ventures into conjecture. stacking hypotheses atop one another. Still, the chemistry speaks volumes. The 7.6 to 1 ratio isn't arbitrary. It sets a limit, a fixed parameter that every origin theory must accommodate. Meeting it calls for either intense alteration across eons or birth in a setting worlds apart from Earth's cradle. JWST's gaze wrapped up in August. The comet edged too near the sun for secure viewing, prompting the scope to pivot to fresh objectives. No follow-ups are slated after perihelion. JWST slots are invaluable, booked far ahead, and the slot for 3I/Atlas has shut. Come what may at closest solar approach, whatever shifts the mix endures under peak heat, JWST won't capture it. We're left to JUICE and earthbound scopes to glimpse the fallout. By that point, the CO2 to water balance may have altered. The coma's blend could have transformed. The August readings from JWST might stand as our sole glimpse of 3I/Atlas before perihelion, rendering that dataset priceless. A molecular signature from a relic of another stellar realm, forged billions of years past. A ledger of volatile levels mirroring inaccessible, unviewable epochs. And a puzzle that deepens with scrutiny. For an 8:1 split isn't merely odd. It's a beacon, a flag signaling an event here unlike anything in our galactic neighborhood. Natural or crafted, chance or intentional, the riddle clings fast. Chapter 5. Mars encounters the intruder. October 3, 2025. 3I/Atlas glided by Mars at 29 million kilometers distant. To put it in perspective, that's about 77 times the Earth-Moon span. On a cosmic scale, it's intimate. Near enough for ESA's Mars satellites, built to image iron-tinged stone scientists on Mars-orbiting probes, positioned just a couple hundred kilometers above the surface, could swing their gear toward the heavens and snag glimpses of the interstellar wanderer as it hurtled across the red planet skies at 67 kilometers per second. The trace gas orbiter from ExoMars delivered the sharpest captures. Its Cassis instrument, designed for color and stereo surface photos, snapped a sequence of shots from October 1st through the 7th. These pics don't dazzle like Hubble's masterpieces. Comet 3I/Atlas shows up as a blurry pale speck, a bit stretched out, drifting over a backdrop of streaked stars. Those trails form because Cassis locked onto the comet's path, adjusting for its speed against the probe's frame. Every shot lasted 3 minutes. Layer them into a sequence, and you've got a basic little video. The speck slides down the view, with its coma standing out as a hazy glow spanning thousands of kilometers. No visible tail, or none strong enough to cut through the background clutter anyway. Nick Thomas, the lead on Cassis, conceded that pulling off these observations was tough. The comet's about 10,000 to 100,000 times dimmer than their typical focus, Mars itself, which bounces back plenty of sunlight from nearby. Aiming that same lens at a faint interloper 30 million kilometers off is akin to peering at the distant skyline through a magnifying glass. The setup wasn't built for such faint targets. Timing for exposures didn't fit, sensitivity hovered on the edge. Still, they nailed it. A few pixels of glow, a soft patch of brightness. Proof that 3I/Atlas was right on the orbital predictions, behaving just like a comet nearing the sun. The veteran Mars Express, ESA's earlier orbiter, gave it a try too, but the comet stayed too elusive. Its high-res stereo camera drew blanks. The Omega and Spicum spectrometers hunted for telltale light patterns, yet the signal barely rose above the static for clear results. They possibly picked up a whisper of an emission or a faint dip in the spectrum, but the readings remain murky, nothing solid yet. Mars Express's true payoff lies in the setup details. Pinpointing the probe's position, the exact moment it scanned, and the scope of its view provides key limits. If 3I/Atlas had shed bits during the close pass, if chunks broke off the core, Mars Express would have spotted them. Seeing only the main body means no breakup happened at that point. The comet held together. NASA's fleet of Mars satellites tuned in as well. The Mars Reconnaissance Orbiter, boasting its high-rise camera, had the pixel power to maybe resolve the nucleus head-on if the angles cooperated. At the nearest point of 29 million kilometers, that works out to about 30 kilometers per pixel for high-rise. With the core pegged at 5 to 6 kilometers wide, it'd be a sub-pixel blur. The nucleus might pop as a hot spot of light, a single saturated dot amid the fainter surrounding haze. But it ought to show if the settings and aim were spot on. So far in this update, no high-rise shots have hit the public feeds. That's standard procedure. Handling data from Mars satellites involves build-up, beaming down during available slots, running through adjustment processes, and finally archiving for all to see. Delays of weeks or months are routine, but the holdup has sparked rumors. Bits of the online world claim NASA is sitting on info. That high-rise caught something odd, and the pics are under secret review before any announcement. Pure fiction. NASA operates openly on these Mars projects, with set rules for sharing data. It all surfaces in time. The wait stems from logistics, not cover-ups. Yet the buzz underscores a key shift. Folks are tuned in. 3i/Atlas has gripped the public's curiosity like no 1i/Oumuamua or 2i/Borisov before. Could be the moment's alignment. Or perhaps Loeb's bold ideas, spinning a story that hooks sci-fi enthusiasts. Or simply that platforms like social media have evolved, pushing obscure science into the spotlight. For whatever cause, the October 3rd swing-by transcended astronomy. It marked a pop culture beat. Suddenly, telescope novices are geeking out over trajectories, light breakdowns, and what sets a comet apart from some alien probe. The Perseverance rover, parked in Jezero crater under NASA, took a stab at skywatching too. Its Mastcam-Z lenses handle celestial targets on Mars, stars, Phobos, Deimos, solar occultations. Theoretically, they could have nabbed 3i/Atlas if it shone bright and climbed high enough during the rover's active hours. On October 1st, a bunch of Mastcam-Z frames picked up a subtle dash overhead. Astrophotographer Simeon Skirm stacked and boosted the contrast on those. The outcome reveals a vague blur right where models predicted 3i/Atlas. It's suggestive, not ironclad. It might stem from a cosmic ray strike. Or perhaps it's just glitches from image compression, though the spot lines up perfectly. The moment fits too. Should it prove genuine, this would stand as the sole surface-level glimpse of an interstellar visitor ever snagged from an alien world. Avi shared it online, citing it as proof that the comet remains traceable, detectable, accessible to current gear if we simply aim it correctly. Skeptics fired back. The mark's too dim, too vague. Bold assertions demand ironclad backing, and a blur plus a composited shot doesn't meet the standard. Yet the argument itself holds worth. It compels folks to dive into the evidence, to scrutinize what separates solid fact from mere potential, to wrestle with the doubt that marks the frontier of breakthroughs. China's Tianwen, one probe and the UAE's Hope orbiter hovered close to Mars amid the pass. Each packs imaging gear and analyzers. In theory, both could have spotted 3i/Atlas. Nothing from those efforts has surfaced so far. Tianwen, one follows distinct data release rules compared to NASA or ESA setups. Findings trickle out via scholarly articles and media announcements on schedules that clash with Western norms. Hope offers more openness, though its core focus lies in planetary atmospheres, not tracking distant wanderers. Should valuable insights emerge from either craft, they'll come to light in time. Still, quiet doesn't signal nothing there. It's simply how global space efforts unfold, with spotty teamwork and shifting agendas. The Mars encounter was bound to be a fleeting glimpse, a narrow slot when alignments clicked and scopes could tilt upward prior to resuming main tasks. Yet that glimpse verifies key aspects. 3i/Atlas held together. Its envelope glowed vividly and dynamically. The path aligned with forecasts, accounting for observational margins. No debris, no extras, nothing hinting at more than one lone icy body arcing hyperbolically, behaving as comets typically do, save for a single overlooked facet that stays unspoken in public but lingers in hushed talks. The envelope exceeded projections. Given the sunlight intensity at that range and the projected core dimensions, it ought to have spanned roughly 2,000 to 3,000 kilometers across. CASIS shots indicate 4,000 to 5,000 kilometers. That's no vast gap. Envelope measurements carry inherent fuzziness. They hinge on imaging duration, sensor capabilities, and how one delineates the edge from the void. But it's bigger than simulations forecast, bigger than expected if vapor release ties straightforwardly to solar warmth. What's causing the excess? One theory points to a livelier core than thought. That 8% active surface might underestimate it. Perhaps 10% or 12% is venting materials, fueling a grander envelope than anticipated. A second idea involves the surrounding frost shards. Those bits drifting within the haze, each evaporating on its own, could swell the overall vapor zone past the core alone. The third notion, the one experts avoid uttering, yet it bubbles up in off-record chats, suggests 3I/Atlas acted up near Mars, ejected stuff, expelled fumes, executed a shift that boosted envelope output briefly. Zero proof backs this third scenario. Zilch. But lack of proof isn't disproof, and the Mars pass marked the final sharp look before closest solar approach. If change loomed, if instruments launched, pieces split, or the body shifted from quiet to bustling, that interval made sense. Near enough to worlds for intrigue, distant enough from the sun for thrifty adjustments, shielded from Earth-based eyes, yet scannable by Mars-based probes. Spotting a routine comet with a marginally expanded envelope from those orbiters feels both comforting and aggravating. Comforting since it aligns with prior models. Aggravating because the mild expansion leaves room for varied readings without pinning down a single truth. One additional Mars-sourced clue awaits deeper scrutiny. The Nomad instrument aboard the Trace Gas Orbiter didn't merely photograph 3I/Atlas. It gathered spectral readings, crude ones, muddled by stray light and gear static, but readings all the same. Processing continues. The crew tackles alignment tweaks, straining to pull a clear signature from records not designed for such a dim, swift quarry. Success here, if Nomad nabbed emission signatures from the envelope mid-pass, would yield makeup details from an utterly fresh angle, unlike JWST, Hubble, or Sphere Vantage. Altered sightlines, shifted lighting phases, unique glow setups. Compounds appearing in Nomad's files could match up with prior scans. Compounds absent from things that ought to be present yet aren't can turn out to be fascinating. The outcomes won't arrive overnight. Spectral examination demands meticulous labor. Extended periods of dedication are required to draw valuable insights from scan information. Yet the group remains driven. This represents the sort of data collection that shapes professional paths. A rare opportunity to examine an interstellar comet via Mars-based observations at its nearest pass. Should they derive significant findings from those cluttered readings, the anticipation will prove justified. Beyond that, Mars offered another benefit. An evaluation of the navigation and synchronization procedures. 3I/Atlas traveled swiftly, at 67 kilometers per second in relation to the Sun, albeit at a reduced pace compared to Mars owing to gravitational dynamics. Aiming a satellite sensor at a shifting objective calls for exact positional forecasts, ongoing adjustments, and impeccable synchronization. The Mars satellites executed it flawlessly. Cassini snagged the comet precisely in the middle of the image. Such achievement confirms the techniques. It demonstrates our ability to synchronize data gathering from various probes and organizations, all zeroed in on an entity that offers no do-overs. And that's crucial come November. As JUICE monitors post-perihelion activity, the teamwork will matter even more. The comet may shine brighter, yet it'll also exhibit heightened activity, possible breakup, and inconsistency. JUICE demands precise positional data refreshed live, drawing from terrestrial sightings and trajectory computations. The Mars encounter served as the final practice run. JUICE marks the primary spectacle, with all knowledge gained from the October 3rd sessions, every alignment technique, adjustment protocol, and information handling process, channeling ahead to maximize the scientific yield from November's efforts. 3I/Atlas has now departed Mars' vicinity. The alignment has altered. The comet has ventured farther into the solar system's core, nearer to the Sun, and more distant from the Crimson World. The satellites have resumed their standard operations, charting terrain details, probing air layers, hunting for hidden moisture. The fleeting interruption from an extraterrestrial guest has faded, leaving Mars solitary in its path, poised for the subsequent brush with an outsider. Chapter 6. Might it disintegrate? Comet splitting isn't uncommon. It's hardly an anomaly. Numerous comets have come apart over documented time. Some dramatically, others subtly, yet all adhering to a sequence that experts grasp fairly solidly. Heat-induced strain fractures the core. Vapor release builds inward pressure. Spinning and gravitational pulls tear apart loosely held components. What was once a single comet transforms into a dispersed comet cluster. We record it, dissect it, and log it among the items unable to endure their solar closest point. 3I/Atlas bears no duty to endure. That point must be emphasized. This entity clings together via such feeble gravity that a quick walk could break free from it. A body that has endured temperature swings from nearly absolute zero to whatever heat it absorbed over eons drifting through the cosmos. A structure that's spongy, cracked, and full of gaps where gases once resided before evaporating in past star system brushes we remain ignorant of. Overall stability remains doubtful. Unity is tenuous. The force holding the core together registers in mere newtons, far from megatons. Thus, the issue isn't if 3I/Atlas might shatter. It's if it will, and the resolution depends on elements beyond Earth's detection reach. Consider past examples. Shoemaker-Levy 9 stands out, spotted in 1993, already split into over 20 separate chunks aligned like beads along its trajectory. The division occurred in 1992 near Jupiter. Gravitational stresses overpowered the comet's resistance. The core tore open. When we found it, the splitting was done. 18 months on, the pieces slammed into Jupiter in a chain of strikes that scarred the gas giant darkly for months. The biggest chunk unleashed power matching 6 million megatons of TNT. Not from blasts, merely motion energy. Mass times velocity squared over 2. Science ignores your unease. Still, Shoemaker-Levy 9 belonged to the Jupiter orbit group. Compact, feebly linked, pre-damaged by prior loops. 3I/Atlas is bigger, more compact, and this marks its sole inner solar system traverse. Varied conditions, varied hazards. Comet 73P/Schwarzmann-Watchman 3 split in its 1995 showing, then again in 2006. Each solar near-miss shed parts. By 2011, counts revealed more than 60 separate bits, mostly minuscule. Each trailing paths akin to the original, nudged by separation speeds. The original core persists, circling on, but reduced, worn down, shedding substance per solar closest approach until only a rubble trail lingers. A future meteor display when Earth intersects that path ages hence. Comet C/2 in April 2020. The Comet C/2019 Y4 Atlas broke apart, despite bearing a confusingly similar name to 3I/Atlas, though the two have no connection whatsoever. As it neared its initial perihelion, the object grew brighter, just as anticipated, sparking enthusiasm among hobbyist stargazers who hoped it would soon shine bright enough for unaided viewing. Suddenly, it began dimming at an alarming pace. Over mere days, its solid core transformed into a diffuse haze of tiny debris pieces, each too minuscule to distinguish on its own. Observations from Hubble captured the disintegration. The bits dispersed, grew fainter, and eventually vanished. The comet no longer functioned as a unified body. The cause of C/2019 Y4's splitting remains a mystery. It hadn't yet ventured too near the Sun. Disruptive tidal effects were minimal. Its spin rate wasn't unusually fast. The leading theory points to thermal strain. Intense warming on the sun-facing surface contrasted sharply with the frozen dark side, leading to uneven swelling. This imbalance fractured the core. Once a fissure formed, escaping gases widened it further. Sublimating ice generated forceful bursts that hastened the split. The breakdown escalated quickly, resulting in total collapse within hours or days. Might something similar befall 3I/Atlas? Definitely. At perihelion, the heat disparity will be intense. One hemisphere scorched by unrelenting sunlight, the opposite shrouded in chill darkness with little warming. Across its 5 to 6 kilometer span, temperatures might differ by hundreds of Kelvin. Such extremes breed structural tension. Factor in the buildup from carbon dioxide turning to gas, occurring precisely under the conditions 3I/Atlas will face, and the setup mirrors a potential shatter scenario. Yet, there's an opposing view. 3I/Atlas has shown activity for months, dating back to at least June via pre-discovery photos revealing a subtle envelope. It's been venting steadily, dissipating built-up gases and wearing down its exterior bit by bit. This gradual wearing could actually avert a sudden rupture. Imagine it as a safety mechanism for releasing pressure. If vapors can seep out consistently via surface openings and fissures, internal forces stay in check, never surging to critical points. The comet discards its icy materials at a measured pace, shedding weight without losing overall cohesion. Evidence comes from its rotation, a steady 16 hours, neither accelerating nor decelerating. Uneven venting or lopsided jets would alter that spin through applied twists on the core. The consistent pace implies even venting and uniform wearing. The core isn't ripping itself due to its emissions. Size plays a role too. Bigger comets resist breaking more stubbornly. Gravitational pull grows with volume, while material strength ties to surface dimensions. For something 5 kilometers across, even if loosely packed with ice and grit, self-attraction prevails. Escape speed is just a handful of meters per second, yet sufficient to keep loose aggregates intact amid typical spinning and gas releases. Overcoming that hold demands a strong jolt, a massive flare-up, an impact, or a gravitational brush nearer than what 3I/Atlas will encounter. Unless the core is pre-damaged or weakened, more a jumble bound by mere contact than true bonding. Then, slight pressures might spark a divide. The pieces wouldn't explode outward dramatically. Instead, they'd separate lazily, paths diverging gradually over days and weeks from orbital variances. Viewed remotely, the comet would seem to blur, its center losing definition, the envelope turning uneven, with eventual clusters of glow spots emerging, distinct brightness lumps, each piece tracing a near but not exact path from the parent orbit. Indeed, ExoMars images dated October 3rd detect no signs of splitting then. The core shows as a lone light patch, though clarity was limited. If bits had drifted just kilometers apart, Cassis couldn't pick them out. They'd merge into a single vague smudge. Verifying wholeness requires sharper views after perihelion, a job for Juice. Now, ponder Lowe's differing take. Suppose the breakup isn't accidental? Imagine a central craft hitting perihelion and dispatching numerous scouts. It would mimic a comet crumbling from heat strain, optically speaking. A single form yields several bodies. They trace spreading paths. Their glow fluctuates as they rotate, altering sunlit profiles. Every aspect fits natural causes. Every bit could also stem from purposeful launch. The key lies in subtleties. Organic debris arcs follow physics alone. Position stems solely from separation speeds and ambient gravity. Newtonian laws let you forecast each piece's spot. No shocks. Released scouts, however, might adjust course. Equipped with drives and navigation in interstellar objects like these, the capacity to alter their paths post-separation stands out. Should any fragments deviate from expected ballistic trajectories, speeding up, slowing down, or shifting course, that signals a clear technological marker beyond doubt. Lowe has dubbed this the dandelion idea, an originating vessel releasing offspring. Every offspring is scout equipped with detectors and relay gear. The organic parallel is intentional. Dandelions don't position their offspring with care. Instead, they fling them into the breeze, betting on volume rather than accuracy. The majority touch down in barren ground and perish. A handful encounter ideal spots and flourish. For an advanced society scanning the cosmos, the approach mirrors this. Launch a swarm of scouts. The bulk malfunction or detect no value. Several hit pay dirt and relay findings. Each scout costs little. The payoff could be vast. Assuming 3I/Atlas adheres to this pattern, perihelion marks the release phase. The scouts fan out. They harness solar pull plus their built-in drives to head for designated worlds. Earth, Mars, Venus, perhaps Europa or Enceladus should the plan involve frozen satellite probes. Every scout bears a set endpoint and sufficient propellant to get there. In mere weeks or months, they touch down, start scanning, send reports to the parent craft prior to its departure from the system out of signal reach. From Earth's vantage, it resembles a comet splitting. We dissect the bits, plot their paths, issue studies on heat strain and material breakdown. Yet we overlook the true events unfolding live, blinded by our presumption of ordinary mechanics over engineered action. That's Lowe's dire vision. Not merely that 3I/Atlas is artificial, but that it is, and we bungle the clues due to overlooking key indicators. We've devoted ages to comet research. We're experts on how they splinter. That expertise skews our lens. Spotting debris, we default to organic explanations. Breaking free demands focused work. Hunting irregularities, monitoring pieces with extra vigilance beyond standard comet splits. Scanning for path shifts, thrust bursts, any break from pure inertia. JUICE handles portions of this on autopilot. The probe locks onto dynamic objects. It computes positions over time. If a piece strays from forecasts, the system alerts, though it's tuned for minor drifts from gas vents, not major redirects via engines. The bar for spotting oddities suits natural bodies. It's unclear if that's sharp enough to detect scout launches. No one's run the trial. No need arose. One further factor, whether 3I/Atlas fragments by chance or design, the main subject vanishes. Debris glows fainter, tougher to follow. Spectral analysis grows trickier as the light scatters over scattered items. The chance to examine a whole extrasolar core evaporates. Purely from science's angle, splitting spells disaster. No more straightforward insights into makeup, build, mass. Just a rubble haze. Fascinating, sure, but no untouched specimen as desired. Yet if it holds together, if 3I/Atlas endures perihelion as one solid unit, we claim that specimen. JUICE eyes it come November. Earth-based scopes catch it in December. We shadow its path beyond Venus, beyond our orbit, into the belt and farther. We observe its dimming as range and waning sunlight halt the jets. We record the tails shift, the hazes fade, the slide into quiet, gleaning all before it hits Jupiter's path in March and vanishes eternally. Thus, the puzzle persists. Will it shatter? Resolution hits in November, with JUICE's initial post-close-up glimpse. When we check if 3I/Atlas remains unified or splintered, if the core held or crumbled, if this tale closes with strewn remnants fading out or persists via a whole body hauling mysteries into the void ahead. Chapter 7. The 10 Billion-Year Voyage. Zabia Perez Cuddo and colleagues at the University of Acarana backtracked the path. 10 million years of orbit modeling, drawing on Gaia measurements of star locations and speeds. They sought near misses. Stars potentially nudging 3I/Atlas across its extended galactic wander. Stars that might trace to its birth system. Instead, they uncovered something disturbing. 0 disruptions. 93 possible star brushes pinpointed. 62 deemed solid bets. None altered the comet's route significantly. Consider the implications. 10 million years cruising the galaxy's plane, amid dense star fields, gas veils, molecular barrels through stellar clusters, and the dense coils of spiral arms, where stars bunch up tightly and gravity's pull turns inevitable. Yet 3I/Atlas sailed right through it all, barely phased, like a projectile zipping at 60 kilometers per second against the local standard of rest. Way too swift for any gravitational traps to snag it. Far too hefty for radiation pressure to nudge its course. Pure inertia propels it along a trajectory that stayed remarkably steady over spans exceeding the entire span of human history. Speed is the crucial factor here. In the galaxy's reference frame, 3I/Atlas clocks in at 58 kilometers per second. By contrast, the Sun circles the galactic core at about 220 kilometers per second. Stars nearby in our cosmic neighborhood travel at roughly those velocities, with deviations of 20 to 30 kilometers per second. 3I/Atlas isn't merely in motion. It's traversing in a distinctive manner. Its path doesn't align with the surrounding stellar stream. Rather than joining the smooth spin of the galactic disk, it slices through that whirl at a sharp incline, signaling origins from elsewhere, a realm with contrasting motion patterns and orbital traits. The thick disk stands out as the prime suspect. That layer of veteran stars embedded above and below the slim disk that hosts our Sun. Those thick disk dwellers emerged in the galaxy's infancy, back when the Milky Way was compact, turbulent, and far from the tidy spiral it boasts now. They loop around with greater speeds at right angles to the plane, plunging repeatedly in and out of the disk instead of hugging its plane. On average, their metal content runs lower, since they coalesced from primordial gas untouched by cycles of stellar explosions. Matthew Hopkins and the Ottawahi Oxford Group conducted models. They drew on stellar populations, galactic architecture, and motion studies. Their findings, shared in a preprint soon after the object's detection, pegged a two-thirds chance that 3I Atlas hails from the thick disk. No guarantees, no ironclad evidence, just a solid odds based on path tracing and speed alignment. In astronomy, though, two-thirds odds signal strong assurance. Enough to shape theories, enough to fuel forecasts. Should 3I Atlas stem from the thick disk, it's ancient. Starbirth there wrapped up roughly 10 billion years back. A comet flung from such a system would have roamed for the bulk of the universe's lifespan so far. Our own solar setup dates to 4.6 billion years. 3I Atlas might easily double that antiquity. It could have taken shape when the cosmos was under 4 billion years young, amid the height of star-making frenzy galaxy-wide. Back in an era when the starry backdrop differed profoundly from today's. A full 10 billion years marinating in the interstellar void. A decade of cosmic radiation pummeling. Rays from across the galaxy, high-energy bits boosted by exploding stars and quasar engines, crashing into the surface near light speed. Every strike unleashes power, snaps molecular links, and chips off particles across eons akin to planetary epochs. Where builds up relentlessly. Outer crusts were thin. Molecular makeup shifts. Once sharp ice crystals turn to disordered mush. Fresh frozen remnants from a newborn disk around a star morph into battered stuff that's worlds away from its starting state. All except the core depths, where rays can't burrow endlessly. In icy material, a standard galactic cosmic ray proton halts after mere meters, or perhaps dozens for the most potent ones. Still, a 5 km wide core offers ample barrier thickness. The heart, shielded by surface overburden, stays untouched and original. A frozen vault holding the elemental recipe from a stellar cradle in the Milky Way's youth. That's why 3I Atlas holds such immense scientific value. It's not simply aged. It offers a tangible relic from the galaxy's dawn. A fragment of a formative disk that birthed a comet as the thick disk still churned out stars. Our grasp of that time relies on roundabout glimpses. Glow from far-off galaxies sketching the ancient universe, or dissecting the makeup of Milky Way elders to guess at the gas clouds of their birth. Digital recreations of cosmic growth that mimic what we see, yet brim with guesswork. But 3I Atlas is real matter, not a model or a faraway peak. A concrete body we can aim scopes at, loaded with molecular markers etched at its genesis. Isotopic balances, carbon-based compounds, ice grain patterns, each one locking in clues about that ancient disk setting. In this light, the CO2 to water proportion of 8:1 carries extra weight. It's more than quirky. It's a clue to the birthplace conditions. It hints that the home system featured particular traits, like elevated carbon levels compared to oxygen, or the temperature variation in the protoplanetary disk positioned the comet's birthplace just past the carbon dioxide frost line, yet in an area rich with accessible carbon. Such circumstances could be typical in dense disk setups or perhaps infrequent. We simply lack the data. 3I Atlas represents our initial comet from a thick disk. With just a single example, it's a vast improvement over having none at all. Prior to 3I Atlas, our understanding of thick disk planetary and cometary groups relied entirely on theory. Simulations suggested that those primordial stellar setups expelled comets and asteroids much like contemporary ones. They forecasted that a portion of those bodies would drift across the galaxy for billions of years. They anticipated that, probabilistically and unavoidably, some would eventually cross into our solar system. 3I Atlas substantiates these forecasts, corroborates the simulations, and demonstrates that the early universe was crafting planets and comets while undergoing the identical chaotic orbital interactions seen in today's star systems. The path examination uncovered an intriguing detail as well. 3I Atlas travels nearly at a right angle to the galactic plane. Its speed along the z-axis, the perpendicular to the plane, stands out as exceptionally elevated. This trait aligns with thick disk bodies. Yet it also implies the comet has been bobbing vertically across the galaxy for billions of years. Every cycle spans tens of millions of years, rising through the thin disk into the galactic halo, descending back through the disk, then ascending once more. a sinusoidal route exposing 3I Atlas to wildly varying conditions throughout its existence. At times, it navigates the crowded disk zones buzzing with star birth and frequent supernovae. There, radiation surges and dust collisions intensify. The comet wears down more rapidly. Other times, it lingers in the halo's sparse voids amid galaxies, where radiation fades and collisions dwindle. The comet enters a quiescent state, where nearly halts. This alternation between severe and gentle surroundings could account for 3I Atlas enduring 10 billion years. The halo intervals allowed recovery, halting mass loss and shielding its core from the ceaseless abrasion of interstellar journeys. Shakru, Kakarov, and Avi released a study comparing the 1I Oumuamua, 2I Borisov, and 3I Atlas. 3 interstellar visitors, each with utterly distinct backgrounds. Oumuamua hails from the thin disk, possibly just 1 billion years in age. Borisov sits midway at about 1.7 billion years, also thin disk origins. 3I Atlas, ancient with a median of 4.6 billion years, but possibly far older, stems from the thick disk. The variety is remarkable. It reveals that interstellar objects form a heterogeneous group. They originate from all corners, spanning every era and galactic sector, each bearing its unique past. And if such variation appears in the mere 3 we've spotted, consider the broader assemblage. The Vera C. Rubin Observatory, once fully active, should spot dozens of interstellar objects annually, potentially even more. Every discovery will carry a narrative, a birthplace, and a galactic path reconstructible via simulations. We can compile an inventory, chart the spread of expelled planetesimals throughout the Milky Way, identify which stellar configurations excel at flinging debris into the void, and pinpoint which galactic areas fuel the roving masses most. 3I Atlas serves as the pioneer, the specimen proving our capacity for this cosmic detective work, locating a comet in July and, by October, formulating a solid theory on its source and age. The margins of error are wide, stretching across billions of years. Still, the approach succeeds. Combining orbital calculations, demographic simulations, and compositional scrutiny yields a tale of origins. Flawed, yet refinable. Periscuto alludes to one additional consequence without dwelling on it. If 3I Atlas has roamed for 10 billion years, it has traversed numerous other star systems. Countless ones, indeed. The galaxy spins. Stars migrate. Across 10 billion years, the comet has come within light years of thousands or millions of stars. Certain stars hosted planets. Some planets may have supported life. And 3I Atlas glided past those setups unnoticed or overlooked, hauling its payload of primordial ice toward the subsequent rendezvous. This prompts an unspoken query. If 3I Atlas encountered other societies, if it threaded their solar realms as it does ours now, what transpired? Did they detect it? Examine it? Dismiss it as mere cosmic debris? Or pursue alternatives? Perhaps inscribing a sign, affixing a device, or leveraging it as a beacon for signals spanning the stars. We possess zero proof of such actions. Zilch. But lacking proof doesn't rule out occurrences from a billion years back or so, amid countless stars whose identities elude us entirely. The 3 Atlas might bear signals, information, advancements, or artifacts left behind by societies that emerged and vanished when our planet was merely a searing lump of lava. We'd remain oblivious without deliberate, focused scrutiny, open to ideas that seem ridiculous at first glance, until you chart the vast timelines and see that ridiculous doesn't equate to unattainable. A span of 10 billion years stretches out immensely, sufficient for realms to ascend and crumble, enough for life forms to develop smarts and then perish, plenty for whole clusters of stars to form and fade. The 3 Atlas has journeyed across every bit of that saga, a quiet observer of cosmic chronicles, and for a fleeting span of months, it's traversing our neighborhood, offering a single shot to decipher any tale encoded in its makeup, form, and perhaps alterations we haven't spotted yet due to our oversight. Its path veers by Jupiter come March, then ventures further past the asteroid zone, outside the Kuiper belt, beyond the heliopause where sun's breeze yields to the void between stars. Returning to obscurity, resuming the perpetual wander among celestial bodies. Already 10 billion years in motion. Another 10 billion ahead before the galaxy morphs into something unrecognizable. And the 3 Atlas will persist, gliding onward, safeguarding its enigmas, awaiting the subsequent society to take note. Chapter 8. Experts resist fiercely. Tom Stadler spared no punches. As NASA's principal researcher on minor solar systematides, he faced a straightforward query on the artificial relic idea at a press session. His reply cut straight. It appears as a comet. It behaves like one. It mirrors in nearly all respects the comets we're familiar with. The double very stress was intentional. This wasn't vague caution. This marked a researcher setting boundaries and declaring a halt. The irritation among astronomers hangs thick in the air. Not due to the inquiries being raised. Curiosity is welcome. Inquiry fuels science. The annoyance stems from the escalation of those queries. From how a slim chance theory gets elevated by news outlets and online forums to match the avalanche of proof favoring a commonplace source. From needing to sift each fresh datum, each spectral reading, each photo through the extraterrestrial gadget lens before genuine research can proceed. Chris Lintott from Oxford pulled even fewer punches. He branded the artificial notion utter drivel propped on flimsy legs, a slight against the compelling efforts to grasp this visitor. Lintott contributed to the group that linked 3 Atlas to the dense disk. He's devoted months to poring over path records, executing demographic models, issuing findings that propel insights into stellar movements and rogue body beginnings. Yet he observes those outcomes drowned out by splashy stories on UFO flagships and tiny scouts. The astronomer's dedication to thorough examination gets eclipsed by conjecture that demands zero backing and yields no verifiable forecasts. Jason Wright of Penn State opted for another tack. He penned an in-depth online essay, methodically tackling every anomaly low highlighted, dataset by dataset. Wright doesn't oppose hunts for tech signs, he pursues them too. He's embedded in the circle hunting traces of alien minds. Still, he's a meticulous researcher who upholds protocols. By those measures, 3 Atlas flops across the board. Consider the luminosity puzzle first. The assertion that initial light measurements hinted at a 20-kilometer span for a regular body. Hence, it has to be artificial. Wright highlights this as selective sampling. Those preliminary scans were coarse, captured when the comet was dim and remote. With superior gear and extended views, the dimensions settled at 5 to 6 kilometers. That's standard data honing, not an enigma demanding wild theories. The assertion regarding absent comet markers in preliminary readings. Wright delved into those studies. The captures were borderline. Signal strength scarcely topped the bare minimum. The lack of distinct chemical bands wasn't evidence of odd makeup. It showed the comet was too subdued for clear analysis at that range. When JWST and top-tier tools zeroed in, the markers emerged. H2O, CO2, CO, carbonyl sulfide, all precisely the lineup you'd anticipate from a comet. The early uncertainty arose from equipment constraints, not the object's true nature. The path odds at 0.005%. Wright crunched the figures afresh. The math hinges largely on your close-pass criteria. Employ sensible spotting limits, factoring in that we detect only items exceeding brightness floors, and the odds climb notably. You're not gauging the likelihood of just any stray body sweeping close to 3 PL, you're figuring the chances that something detectable and luminous swings by 3 planets. That's a far looser criterion. The likelihood remains slim, yet far from ridiculously slim. It's not some 5 sigma outlier. Next up is the matter of dust patterns. The assertion that dust blowing toward the sun demands powered engines or deliberate releases. Wright highlights years of comet research revealing intricate dust setups. Ejections from jets aren't ever even. The tilt of the spin axis plays a role. Differences in nearby frozen materials lead to uneven vapor release. The particular setup observed in 3I Atlas could seem odd, yet it fits inside the spectrum of ordinary processes. Scores of comets in our solar system display comparable traits. No one calls in extraterrestrial engineering to make sense of those. The spin duration claim crumbles on closer look. A 16.16-hour cycle is typical for an object of this scale. It holds steady without risking disintegration. It aligns with formations like loose aggregates or intact cores. It reveals zero about crafted origins versus organic ones, since both exhibit parallel spin behaviors. Treating it as proof of engineering resembles declaring a boulder man-made just for being spherical. Sphericity might arise naturally or through crafting. Spin rates might emerge organically or via intent. The data point stays neutral. Wright levels his strongest rebuke at the entry path rationale. The idea that arriving from Sagittarius, aligned with the Milky Way's core, was a clever ploy to dodge prompt spotting. This amounts to imposing purpose on mere layout. 3I Atlas entered from there simply because that's its path. Had it hailed from Ursa Major, we'd get claims about why that zone served some tactical edge instead. The reasoning resists disproof. Whatever the incoming route, it gets framed as deliberate. That's not rigorous inquiry. That's narrative crafting. Yet the harshest takedown stems from what's missing if the idea held water. Should 3I Atlas be a crafted device, it ought to give off discarded warmth. Any functioning setup, circuits, or drive system produces thermal output. That warmth must escape via radiation. In the infrared bands tied to temperatures around a few hundred Kelvin, Scope's hunting heat should pick up glows beyond mere sunlight absorption. Numerous IR scans have occurred. Spitzer prior to shutdown. JWST, SphereX, plus earthbound IR arrays. Each reveals warmth levels matching a chilly frozen form heated solely by the star. No surplus, no oddity, merely a comet acting as expected. Should propulsion exist, spectroscopy, chemistry, or path shifts surpassing gas-driven effects would reveal it. 3I Atlas has faced non-stop monitoring since spotting. Its path is mapped with fine detail. Any straying from pure gravity's pull would stand out. Nothing of the sort appears. The object adheres flawlessly to classical physics. No thrusts, no adjustments, no signs of guided motion. If signals flow, we'd catch them. Radio waves, laser bursts, flickering beams. SETI efforts have tuned in. Various radio dishes have aimed at 3I Atlas as it neared. The Greenbank dish, Allen telescope setup, Parkes in Australia, all sweeping broad spectra for traces of engineered transmissions. Outcomes: quiet, absolute, utterly so, without even vague static open to loose readings, just cosmic static minus any synthetic trace. All checks capable of separating engineered from innate have run their course. All return voids. Eventually, proof's onus pivots. Mere nods to rare alignments no longer suffice to insist mundane accounts cover them. Positive signs demand entry. A spotting, a reading, an element defying comet norms and calling for engineered input. Such signs are absent. Statler drove this home clearly. We wield top-tier tools. We've scrutinized 3I Atlas closely for months. Anything truly outlandish, any shatter to the comet framework needing fresh laws or odd groupings, would have surfaced. Its absence counts as data, not ironclad, but data leaning hard toward innate roots. The expert circle's reply stays balanced yet resolute. Studies appear in journals, findings circulate, watches persist, but a quiet consensus holds that the crafted idea merits no deep pursuit now. It's undergone trials. It flopped. Lingering arguments divert from the real research prospects 3I Atlas offers. And those prospects loom large. Our initial dive into a thick disk wanderer. The debut find with an 8:1 CO to 2:1 mix. The pioneer interstellar guest eyed by JWST, SphereX, and Mars satellites all at once. Just the makeup of this object could sharpen our models for how planets form in old stellar environments. Insights from its path enhance what we know about how galaxies move and how objects get flung out. The way it's releasing gases questions our ideas on comet behavior and how volatiles are spread. Yet all these insights fade into the background whenever discussions loop endlessly around alien spacecraft. Researchers are exhausted by it, worn out from the effort of refuting assertions that never deserved attention in the first place. Frustrated seeing their research overlooked simply because it lacks drama. Irritated by suggestions that they're narrow-minded for demanding solid proof before embracing wild ideas. Lindot's remark on the offense hits home. The groups behind 3 Atlas include top-tier astronomers globally. They're wielding state-of-the-art tools, sharing findings in leading publications, and carrying out the core of scientific method. watching closely, examining data, forming judgments from evidence, only to hear they're overlooking the plain truth, too attached to standard views to notice what's staring them in the face. It's maddening. Beyond that lies a bigger issue. From this saga, the general public walks away believing experts brushed off the extraterrestrial idea without real scrutiny. That's completely reversed. The probe was thorough. Various groups, diverse tools, extended months of labor. The notion was handled with gravity, scrutinized intensely, and deemed unconvincing. But since the checks involved complex details and negative outcomes didn't make big news, folks see scientists as arrogant instead of meticulous. Such a view harms the field. It bolsters the notion that established astronomy clings too tightly to the status quo, shies from big changes, and guards old ideas fiercely. Nothing could be further from reality. Stargazers would celebrate uncovering signs of alien tech. It'd mark the breakthrough of the century, earn Nobels, overhaul books, and reshape our cosmic perspective entirely. The drive exists, the eagerness is real. What's absent is proof. Wright captured it perfectly in his online entry. Bold assertions demand bold evidence, not the reverse. The process isn't about forcing everyday answers or total assurance before eyeing options. It builds through gathered facts, pursuing them no matter the direction. For now, every clue points to a comet, a peculiar one, a fascinating one, a data-rich one, but still a comet. Observations of 3 Atlas will persist into November and December. Due STA is set for February. Should truly odd features emerge? If the after-closest sun checks uncover actions defying natural causes, the debate will shift. Experts will adjust. Fresh ideas will surface. Predictions ready for testing will follow. That's the path science takes, via data, not guesses. For the moment, the tech theory stays as it started, a slim chance, lacking backing, propped up by wishful logic over hard facts. And the astronomers tracking 3 Atlas keep at it, recording this standout from the galactic halo, pulling out all possible details before it vanishes into the void again, alien story or not, buzz or no buzz. That's the essence of their role. Chapter 9. Social media erupts. The frenzy kicked off on TikTok. A clip uploaded on September 29th featured intense tunes layered on generic clips of comets and probes. On-screen words asserted 3 Atlas hurtled toward Earth. NASA suppressing facts. Strike due October 22nd. It racked up 2 million views within 2 days. Thousands of reactions. Folks sketching escape strategies, wondering about fleeing, scouting bunker ranges. All from pure invention. Dismantling the crash story was straightforward. 3 Atlas's nearest pass by Earth stands at 1.8 astronomical units. That's 270 million kilometers, over 1.5 times the planet's solar span. It stays far away. The flight path details are out there. NASA shares position tables. Basic programs let anyone confirm the route, yet truths lag behind terror and virality. Counter clips reached a few 100,000 plays. The alarm one lingers on, still drawing replies from those viewing October 22nd as apocalypse. Next up, the psychic visions. A profile named New York Crypto King shared on X that they'd psychically scanned 3 Atlas. They described spotting frameworks within, tiny organisms tucked in frozen compartments. A transmission at undiscovered wavelengths. The entry spelled out the core makeup, the setup of tech parts masked as ordinary stuff. A cautionary message circulated about probes launching on October 29th, releasing microorganisms into Earth's air as elements of a planetary reshaping effort. The notion of remote viewing qualifies as pseudoscience. Rigorous tests have consistently demonstrated its ineffectiveness. No individual possesses the ability to psychically observe far-off items, yet the message gained momentum regardless. It amassed 30,000 likes and 15,000 retweets. Folks regarded it as reliable intel, constructing elaborate hypotheses and linking it to broader conspiracy narratives. The assertion regarding the signal proved especially contagious. Several hobbyist radio operators began scanning channels they believed could transmit the transmission. They detected zilch, yet persuaded themselves that the signal employed encryption or advanced modulation techniques surpassing current human capabilities. The 4chan forum joined the fray via a thread purporting internal expertise. An unidentified poster posing as a European skywatcher declared that 3Y isn't a comet or spacecraft. Rather, it's a remnant sphere of dark matter or dark energy from the universe's origin. The entity fails to bounce back sunlight. It draws power from the quantum vacuum. It's en route to Earth to fuse with the planet's nucleus and initiate a shift in dimensions. The thread was patently invented. The science defied logic. Dark matter doesn't coalesce into spheres. It can't extract energy from the vacuum. Still, screenshots proliferated across sites, circulated as if they were pilfered secret documents. The link to Jeffrey Epstein surfaced in early October. A Reddit user spotted that Lowe's initial significant study on 3 Atlas came out 72 years following Epstein's birth. They computed that the comet's detection on July 1st held numerological weight. They tossed in selective ties between its path details and key moments in Epstein's timeline. They wrapped up that the whole 3I Atlas phenomenon was fabricated to divert focus from fresh scrutiny of Epstein's documents. The plot lacked coherence. Comets aren't unveiled on scheduled days to advance political schemes, but it propagated nonetheless, merging into QAnon lore and referenced as proof of elite interference. Additional spins zeroed in on Loeb himself, with claims that his breakdown of 3 Atlas was invalidated due to his Jewish background, Israeli ties, or Harvard's backing from whatever international foe the author aimed to highlight. These weren't sincere critiques. They masked anti-Semitic barbs as doubt. Loeb countered them in a blog entry, stressing that 3 Atlas stands apart from his personal background, that anybody equipped with a telescope can spot the body, and that his roots and citizenship hold no sway over the science. But debating prejudice wears one down. The attacks persisted. The NASA funding lapse turned into a key discussion thread. In early October, the U.S. federal closure kicked off. NASA's outreach team halted site and social updates. Announcements tapered off. This brief info gap overlapped with 3I Atlas nearing Mars and vanishing behind the Sun. Plot proponents perceived intent. The closure was engineered. A ploy to block NASA from fielding inquiries on Mars probe observations during the pass. The organization was burying findings, concealing photos revealing breakup or probe launches or other unwelcome revelations. Truthfully, such closures stem from partisan breakdowns, not orchestrated concealments. They occur amid stalled fiscal talks. The overlap was happenstance. NASA had no secrets. Mars probe info normally requires weeks to analyze. The closure extended the wait, but due to furloughs halting operations, not suppression. Once funding resumed, the visuals emerged. They depicted a standard comet. Yet the storyline had solidified. Any postponement confirmed intrigue, no matter the eventual revelations. A laser's standard verification team probed rumors spreading on Arabic online networks. Threads asserted that 3I Atlas would collide with Earth on October 22nd, that its trail would toxify the skies, that pulses from the comet would cripple worldwide devices, that ancient prophecies foretold it, and that omens were converging. Sannard followed the origins to garbled translations and intentional lies, issuing thorough refutations backed by origins and specialist insights. The correction likely hit just 10% of the exposure the initial hoaxes garnered. A buzzing Facebook entry alleged that 3 Atlas sparked an urgent armed forces summit. Global figures gathered covertly. Safeguard protocols activated. Fabricated statements from anonymous Defense Department sources implied the comet endangered security. The entry connected to a YouTube clip. It racked up 3 million watches, spanning 40 minutes. The voiceover detailed how 3I Atlas got picked up by secret defense orbiters. Before everyday stargazers spotted it, details about its path got hushed up at first. Leaks from those in the know trickled out via unofficial routes. But none of that held water. Everything was delivered with brooding soundtracks and a commanding voiceover, lending it an air of legitimacy. The spiritual side took center stage. Posts from Christians framing 3I Atlas as a precursor to the apocalypse. Allusions to the Book of Revelation and ties to wormwood. The comet cast as a messenger of divine reckoning. Muslim writings explored parallel ideas through their own holy texts. Hindu views tied it to vast cosmic rhythms and divine incarnations. Folks from all faiths layered doomsday tales onto what was merely frozen water and stone. Humanity's urge to assign significance to sky phenomena runs deep in history. Comets have long signaled doom. 3I Atlas fits that pattern. Only difference is, these portents now race around the world in mere hours, not crawling through cultures over decades. Online memes fueled the fire. Pictures of 3I Atlas captioned with all sorts of quips, like the assignment I skipped finally catching up to me, or my troubles landing exactly when expected. Extraterrestrial sightseers scoping out Earth, then bailing without a second look. Those jokes were lighthearted and amusing, yet they cemented the notion that 3I Atlas played a role in some drama, not just a hunk of space debris. It gained a sense of purpose, motives, even quirks. Humanizing it that way clouded folks' ability to grapple with the real evidence. Instead of scrutinizing the facts, people connected with the comet on a gut level. The divide was sharp. Scientists and outreach experts pushed out precise details, light spectra, path projections, makeup breakdowns. Against them surged a flood of guesses, plots, dread, and daydreams. The camps rarely crossed paths. They dwelled in separate digital worlds, on distinct apps, with clashing ways of knowing truth. Someone could binge hours of 3I Atlas buzz and miss every solid detail. X's fact-check tags raced to intervene, attaching explanations to hot tweets, directing to NASA's site, offering path stats to debunk crash fears. But those notes only pop up post-buzz, touching just a sliver of viewers. And stubborn biases run deep. Believers in the interstellar craft theory brush off rebuttals easily. NASA's covering up. Experts are too rigid. The straight facts don't compute. Dissenting info just vanishes from their feed. YouTube turned into a war zone. Educational creators broke down what 3I Atlas truly entailed. The sightings revealed, the elements implied. Their clips barely hit 6 figures in views. By contrast, plot-peddling accounts with flashy covers and hype headlines racked up millions. The system rewards clicks over truth. Panic hooks viewers way better than lessons. Thus, the false stuff surges ahead, echoes louder, and cashes in. Reddit boards fractured as expected. The space and astro ones held steady. Mods axed wild theories. Posters refuted nonsense with sources, debating path ambiguities and light analysis techniques calmly. Yet in UFO, plot, and oddball forums, it devolved into bubbles. Doubt earned thumbs down. Ties to established science? Branded as spin. Groups hardened into their views, patting each other on the back for seeing the real deal, while the rest were dupes or in on it. Non-expert Insta-stars dished out bold takes on 3I Atlas sans credentials. Plenty botched the basics, swapping astro units for light years, insisting it was eyeball visible when it wasn't, jumbling it with unrelated sky bodies. Still, they commanded crowds, with follower counts in the hundreds of thousands who bought in, reposted, and ranked their hot air alongside lab-vetted studies. The fake news bit hard in reality. Stargazing teachers swamped with frantic messages. Instructors soothing kids convinced doom was nigh. Counselors handling spikes in worry from end-of-days hype. The harm wasn't abstract. It showed up in hours lost debunking lies and the emotional toll on those at risk. Part of the wild talk was just edgy pranks, savvy types stirring the pot for kicks. But plenty was earnest. Devout fans saw 3I Atlas as alien outreach, planetary peril, or godly sign. Pushback only made them dig in, chase affirming sources, weave intricate webs linking it to bigger schemes. The thing morphed into an icon, a canvas for dumping personal terrors, dreams, or wild imaginings. Come mid-October, 3I Atlas had lost its essence as a mere comet. It evolved into a societal spectacle, a reflection of how communities handle data in the era of online platforms. Where reality merges with invention, where expert knowledge diminishes in value, and where panic outpaces comprehension. The physical entity itself, that 5-kilometer sphere of primordial ice and stone, now concealed on the sun's far side, faded into the background amid the escalating tales encircling it. Meanwhile, the researchers examining 3 Atlas could merely observe. They might release studies, offer media spots, issue clarifications online, yet they held no sway over the unfolding tale. The tale had broken free, transformed, grown into an entity outside their influence. Their only option was to press on with the research, record the findings, scrutinize the information, and hold faith that, well after the digital uproar subsided, the factual scientific archive would endure intact, a steady balance against the disorder. Chapter 10. November's pivotal revelation. On November 4th, JUICE stations itself 428,000 kilometers away from 3 Atlas. That's nearer than any probe will approach in the aftermath of perihelion during the viewing phase. The Jupiter Icy Moons Explorer wasn't crafted for comet scrutiny. Its purpose centers on probing Europa, Ganymede, and Callisto, frozen shells atop hidden water worlds, radiation zones near Jupiter, and electromagnetic exchanges. Yet probes prove flexible. Controllers can adjust course. From November 2nd through 25th, JUICE will allocate slots to monitor the cosmic newcomer, gathering details at a time when Earth telescopes grapple with the Sun's closeness. The array of tools is impressive. Janus, the visual imaging setup, will photograph the core and surrounding haze at superior detail levels unmatched by others in this span. MAGIS, the spectral mapper, will chart material makeup via infrared bands, following the spread of various gases in the envelope. UVS, the UV analyzer, will spot glows from energized particles and compounds, expanding on August's quick scans, but with sharper frequency detail. PEP, the environmental sampler, will gauge the ionized and neutral vapors around 3 Atlas, recording solar wind's effects on the comet's emissions. This marks the key interval. 3 Atlas passed perihelion on October 29th. The outcomes of that solar near-miss, the intense warmth, the height of vapor release, any possible breakup or device release, will show up in November. The comet ought to shine vividly, show vigor, perhaps alter form. JUICE will capture that shift from a position unattainable by terrestrial gear. However, limitations apply. Data link capacity. JUICE employs its mid-range antenna since the primary one doubles as thermal protection now. Transfer speeds drop accordingly. Photos and readings accumulate internally. They transmit later, as schedules permit. November's captures won't arrive on Earth before February 2026. A 3-month delay. 3 months without insight into JUICE's discoveries. Did the comet hold together, split apart, or reveal surprises in the readings? Earth observatories will spot 3 Atlas toward late November, once solar separation widens sufficiently for dusk viewings. As the comet escapes the harshest dazzle and opens to big lens scopes, forecasts differ. Certain simulations forecast brightness at magnitude 10 or 11, visible through 8-inch hobby scopes in clear, dark conditions. Others take a cautious view, estimating 12 to 13, needing pro equipment or focused amateur rigs. The luminosity will instantly signal any big shifts. Should 3 Atlas flare up sharply, if perihelion sparked a huge surge or uncovered new materials, the rating will exceed estimates. In case of breakup, overall glow could rise at first from added exposed areas, then wane as pieces scatter. Should it quiet down, if materials depleted or operations halted abruptly, it'll appear fainter than anticipated. Such details emerge right away from initial ground watches. The Galileo project sites are active. 3 locations scanning the heavens nonstop: Massachusetts, Pennsylvania, Nevada. Through November and December, sensitivity amps up. Any fleeting item, any unknown drifting form triggers alerts. Loeb voiced his hopes openly. Should devices launch at perihelion, employing backward thruster tactics to slot into Earth path, they'd reach between November 21st and December 5th. The sites target precisely those signs: tiny bodies in odd paths, routes clashing with known junk or satellites, hints of engineered design. Odds remain slim, as all agree, but surveillance costs little against the huge gains if confirmed. Should anything emerge, should and when an unidentified object emerges that defies straightforward natural explanations, the entire scenario shifts instantly and profoundly. Telescopes across the globe would swiftly redirect their focus to examine it closely. Space organizations would rush to organize flybys or detailed flyovers. The ranks of scientists would rally with an urgency unmatched since the initial detection of gravitational waves or the verification of the first exoplanet. Should nothing emerge, however, if November and December elapse without any spacecraft appearing, the artificial origin theory forfeits its final pillar. The artificiality score plummets. 3i/Atlas earns a firm label as a natural comet. Exceptionally massive and compositionally odd, yet entirely natural. The conjecture ceases. Research presses on. The narrative evolves into one of exploration and analysis instead of extraterrestrial encounter. The Europa Clipper mission stands ready for possible sightings as well. NASA's Jupiter-bound probe lifted off not long ago. The vessel is en route but hasn't reached its destination. Talks are underway for syncing efforts between Clipper and JUICE. Each equipped with UV spectrometers, simultaneous views of 3i/Atlas from separate vantage points would yield parallax-based stereoscopic data on the coma's form, insights no lone probe could gather. Optimal alignment isn't perfect. Clipper's placement isn't ideal, yet if a window opens, the teams will seize it. True breakthroughs will arise from contrasting conditions before and after perihelion. JWST provided August readings, while Mars-based observatories supplied September ones. Those captures depicted 3i/Atlas nearing its solar closest approach. Still fairly chilly, with outgassing proceeding at steady levels. JUICE and Earth-based scopes in November will capture the consequences. The comet, warmed and strained, might undergo dramatic changes from its nearest sun pass in a 10 billion-year lifespan. Matching those datasets uncovers how such interstellar wanderers react at perihelion, how their makeup transforms, and whether their framework endures or crumbles amid heat stress. The CO2 to water proportion grows especially compelling. It stood at 8:1 in August. Will November show the same 8:1? Or might solar heating have selectively vaporized the CO2, bearing water ice, and altering the balance to more ordinary levels? A shift in the ratio signals a stratified build, CO2, heavy surface layers over a water-dominated core. Stability implies uniform makeup end to end. Either result holds scientific merit, but each paints a distinct picture of the object's origins and development. Tail formation offers further clues. Pre-perihelion photos revealed a subtle tail, or none at all, based on integration time and detector thresholds. Afterward, expect a striking tail, millions of kilometers in length, bent by solar wind forces and orbital speed. Tail analysis via spectroscopy discloses the ejected particles, silicates, organic compounds, frozen volatiles. The spectrum of particle sizes sheds light on breakdown mechanisms. Tiny particles indicate intense evaporation. Bigger ones point to physical breakup or sudden bursts. Should 3i/Atlas splinter, the tail would display intricate patterns, diverse flows, merged features, with each piece generating its own extension, all merging in terrestrial views, but perhaps separable through precise brightness and location tracking. Hubble might, in theory, photograph the tail's details if observing slots open up, distinguishing piece-specific inputs and charting the rubble spread. But Hubble's schedule is tight, oversubscribed by 5 or 10 times over. Securing emergency director's time for additional looks isn't assured. The Vera C. Rubin Observatory remains offline for now. Its debut imaging is months out, but once active, it will transform how we spot and study interstellar intruders. Known initially as the Large Synoptic Survey Telescope, it will sweep the full night sky every few evenings with deep, prolonged exposures and automated alerts for transients. Rubin will snare incoming interstellar travelers sooner, while they're distant and dim. It will monitor them past perihelion and further. It will compile light curves from thousands of measurements. Follow-on spectra from other tools will draw on Rubin's non-stop photometric details. 3i/Atlas serves as the forerunner. This body instructs us on anticipating future interstellar comets, their luminosity patterns, activity progressions, emerging spectral signatures, and timings. Each look at 3i/Atlas shapes Rubin's search strategies, hones spotting routines, and tunes predictive frameworks. The subsequent 3i/Atlas, the fourth such interloper, will get spotted quicker and dissected more thoroughly, thanks to insights from this case. November's data also aids in fine-tuning the path. Each positional fix enhances the orbit calculation, narrowing uncertainties. Reducing uncertainties enables more accurate forecasts of 3i/Atlas's position come December, January, and further ahead. As the comet progresses beyond Venus, crossing Earth's orbital path en route to the asteroid belt once more. Monitoring grows more challenging. It fades in brightness and shifts against denser backdrops of stars. Accurate ephemerides guarantee we won't misplace it. That terrestrial telescopes can aim precisely. That precious observation slots aren't squandered hunting for a target that's meant to appear in the viewfinder but doesn't due to minor positional errors. The JUICE probe's plasma readings stand out as unparalleled. No other mission will venture near enough to probe the interface zone where the solar wind clashes with the comet's gaseous emissions. That frontier, known as the cometopause, remains fluid, ever-evolving with fluctuations in emission levels and solar wind intensity. PEP will gauge ion concentrations, electron heat levels, disruptions in the magnetic field. This information will refine simulations of cometary magnetospheres, particle acceleration processes, and energy transfer within the coma. For 3I/Atlas in particular, the plasma insights could uncover nuanced details on its makeup. Various volatiles break down into ions at distinct paces, generating unique ion types. PEP's mass spectrometer can differentiate water-derived ions, CO2, derived ones, and more. Should unforeseen ions emerge, or if the plasma profile highlights molecules overlooked by remote spectroscopy, that's groundbreaking data. It provides fresh limits on the comet's true constituents compared to our earlier deductions from afar. February 2026 seems far off. 3 months is an eternity to anticipate JUICE's findings, yet it's essential. The probe's data transmission is constrained. Scientific objectives trump outreach efforts. The eventual release will justify the delay, with data refined, calibrated, and scrutinized by specialists versed in the hardware and adept at isolating genuine signals amid interference. Once shared in publications, these outcomes will be authoritative. The most thorough post-perihelion profile of 3I/Atlas achievable under today's tech and operational limits. In the interim, we depend on Earth-based sightings, hobbyists peering through home setups, pro facilities fitting 3I/Atlas into packed timetables, global teamwork on spectral surveys. Each cloudless evening counts. Each data point enriches the collection. Gradually, through successive photos and analyses, the perihelion narrative sharpens into clarity. The comet remains indifferent to our intrigue. It has no awareness of our gaze. It merely pursues its path, venting vapors or lying quiet, whole or in pieces, purely natural or, defying odds, altered in some unforeseen way. 3I/Atlas drifts onward into November, unaware of the scopes following its course, the devices probing its glow, the fierce arguments over its essence. It simply exists, and we, from our modest perch 93 million miles sunward, strive urgently to decipher that existence before the comet slips into obscurity, carrying its secrets away.